So I'm making this video because I haven't really found any intuitive explanation regarding the solution to the Sqrt problem on Leetcode, which is numbered as 69, I believe. So the backbone of the solution, of the optimal solution and quite mathematically beautiful solution, the backbone of it is the Newton's method. And the Newton's method allows us to iteratively find roots of some function f of x. And roots are such x's in which our function is equal to 0. So the algorithm behind the Newton's method states that the next point that is closer to the roots of a function is equal to the current point minus the value of the function in this point divided by the first order derivative in this point. So recall that the first order derivative in x of n is equal to the value of the tangent alpha. So suppose we have some arbitrary function f of x, and we have some x of n over here, and we have a tangent line that intersects f of x in this point. It has only one intersection point with f of x, and this would be the first order derivative. And especially the value of this first order derivative in the point of x of n equals to alpha, to tangent of alpha in particular. So recall also that the tangent of alpha equals to the opposite side of this triangle divided by this side. And we should also denote that the intersection between the first order derivative with the x-axis is also xn plus 1. So the length of this side would equal to x of n minus x of n plus 1. And the tangent of alpha is the opposite side, which equals to the value of this arbitrary function in the point of x of n divided by x of n minus x of n plus 1. So if we plug this inside of the first order derivative in the point of x of n, and we then plug the tangent value in the denominator of this fraction, this would result into the equation that the x of n plus 1 equals x of n minus f in the x of n multiplied by x of n minus x of n plus 1 divided by f of x. F in x of n. So we can further simplify this equation as x of n plus 1 equals x of n minus x of n plus x of n plus 1, which in its turn will result into identity x of n plus 1 equals to x of n plus 1. So it's a quick proof of the Newton's method and how it actually works. But what is the intuition behind it? So suppose we have a simple function which is x squared. So it's a parabola that is defined by the function of x squared. And we obtain our initial point somewhere randomly by picking a random point along the function of x, for example, somewhere over here. This would be our x of 1, which is x of n. Our first approximation of roots of this function. And we need to iteratively find this point, which is f of x equals to 0, which coincidentally enough is also the minimum of this parabola. Hence, sometimes we use Newton's method to find minimum of a function. For example, some might propose using Newton's method in order to find the minimum of the negative log likelihood in finding an optimal solution for the logistic regression problem. So, for example, if we obtain this kind of point and plot a tangent line that passes through this point, something like that, we obtain the next point, which is x of 2. And we then plot another tangent line like that. We obtain another point, x of 3. We plot another line which passes through x of 3, and we obtain the next point, x4, and by doing these operations long enough, we iteratively could possibly find this center point in which the value of the function is equal to 0, and hence we are actually able to find the minimum of x squared. So this is pretty much the intuition behind this method. There is also a great animation on the Wikipedia page regarding the Newton's method, so I very much encourage you to check it out. So how does it actually apply to the Sqrt problem on Leetcode? So let's actually rewrite our problem of finding the best square root for some input number r as an equation. X squared minus r equals to 0. So if it actually does equal to the positive square root of r, then we're able to solve this equation and obtain roots of this function. So since I've said function, we can now define this as a function of x, which is equal to x squared minus r. So now we need to start an iterative process in which we obtain new number all over again, which eventually leads us to finding roots of this equation, roots of this function. So this would mean that the next point would equal to the current point minus the value of the function in this current point divided by the first order derivative in this point, which will equal to 2 multiplied by x of n. So the first order derivative is 2x plus 0 because the input number is a constant. Therefore, if we further simplify this, if we bring all of this under the same denominator, we would have 2 of x of n squared minus x of n squared plus r divided by 2 of x of n. This can be also further simplified as x of n squared plus r divided by 2 of x of n. And we can also rewrite this in a more widely accepted form, which many of you have already probably seen. The next point in this iterative process is equal to 1/2 multiplied by x of n plus r divided by x of n. And this is the backbone of the solution of the Sqrt problem in Leetcode. We set up some loop within which we iteratively find the new approximation for the root of this function until we reach some condition. So how can we actually code it in some language? For the sake of demonstration, I have chosen Python because it's the easiest to understand. And first step is, of course, defining the Sqrt function that takes the input number r. And the next step is actually defining the first approximation. So in our example, the initial approximation would be the number itself, because it will allow us to fairly treat niche cases such as where r is equal to 1. So if we pick an initial approximation that is greater than r, we might do more operations than needed, and if we pick a number that is lower than 1, we might obtain a result that is not a square root of 1, and the result should be 1. We might even obtain a number that is lower than 1. Now we need to start the iterative process. We can use a while loop here under the condition that our approximation x of n squared is greater than r. So basically this tells us to run our while loop to find the minimum of a function, which is also a root of a function, until our x of n squared is actually less or equal than r and is close to the best approximation of the root of a function x squared minus r. So following the previously defined Newton's method equation, the next x of n plus 1 is equal to 1/2 multiplied by x of n plus r divided by x of n. And then we need to return the closest number to the whole number, so return the rounded number using the int operation in Python. However, we might run into some complications here, since the number of floating points in Python is fixed, and we might obtain the same number all over again, and we might run into an infinite loop. In order to demonstrate that, we can define a number of operations, and on each iteration subtract 1 from the number of operations until the number of operations is actually less than 0, and then we break the while loop in order to not run into an infinite one. So if we take, for example, an input number of 20, which has a square root of around 4.47, this would yield us an infinite loop, because at some point the numbers do not change. So we run into an infinite loop because of the fixed number of floating points. So in order to avoid this, we not only need to round the number in the end, but also to round it here by doing a double division operation, which instead of returning a float, returns an int. And this will actually allow us to reach the desired solution, which is the closest number, which is 4.